Welcome back to The Explainer. Today, we're stepping into a highly engineered digital world. Let's totally redefine how you look at maps. We're going to strip away the illusion that a map is just some static drawing or a simple picture of the ground. Instead, we're decoding cartography for what it truly is, a dynamic, sophisticated data interface. Okay, let's dive into this. When you look at a stunning, glowing visualization of the Earth like this, you're not just seeing land and water, right? You're actually seeing raw information that has been meticulously translated into visual code. You literally can't map anything until you know exactly what kind of data you're feeding into your visual dashboard. The source data dictates every single graphical choice a cartographer makes. Here's our roadmap for today's explainer. We'll start with decoding cartographic data, then look at data without order, followed by data with order. After that, we'll master chlorophyll maps, navigate isoline maps, and finally, wrap it all up with multivariate cartography. Let's get into it. Section 1. Decoding cartographic data, the core dichotomy. You see, every single cartographer, before they render even a single pixel, has to face a fundamental fork in the road when looking at their raw data. And this split, it's basically the foundational protocol for encoding maps. You absolutely have to figure out if your data exists without order or with order before rendering. On one side, we've got nominal data. This is qualitative, categorical stuff with zero internal sequence. Think of basic labels like forest, water, or city. But on the flip side, we have ordinal or cardinal data. This is the quantitative stuff. It follows a strict sequence or metric value, like population density or temperature. All right, moving on to Section 2. Data without order, categorical mapping. Let's head down that first branch of our logic tree and explore nominal data, the purely qualitative stuff that exists without any built-in hierarchy. So here's the really crucial point to remember. Because these categories, say a forest versus a city, are inherently equal, adding a visual hierarchy literally causes a system error in the viewer's brain. Seriously, if you use a giant symbol for a forest and a tiny one for a city, or make one bright red and the other a faint pink, your brain instantly, subconsciously assumes one is more or better than the other. To stop that from happening, cartographers have to differentiate this data using varied shapes or distinct color hues that don't imply any sort of rink. And honestly, the workarounds for this are pretty ingenious. If you skip solid colors entirely, you can encode boundaries using distinct line patterns, hatchings, or maybe variably dashed outlines. Just notice how overlapping regional data, like different soil types or land use areas, can be safely and clearly categorized. You get all the info without ever tricking the viewer into thinking one area outranks another. Which brings us to Section 3. Data with order, absolute versus relative. Now we're switching over to the heavier branch, data that actually contains an internal sequence or a precise metric value. So, when we're dealing with absolute values, hard numbers like the exact population of a city, we have two really fascinating rendering protocols. On the left, we've got a proportional sign map. This one just overlays differently sized circles on a fixed geographic borders. Pretty standard. But on the right, that's a value by area cartogram. Instead of just dropping a big circle on the map, the algorithm actually warps and bloats the real-world geographic shapes based entirely on the data's weight. It's wild to look at. And this brilliantly illustrates how geometric scaling works in practice. By tying those absolute data values directly to proportional scaling, raw, abstract numbers are instantly translated into a visual hierarchy you just can't miss. Basically, the heavier the data, the larger the graphical volume. All right, Section 4, Mastering Choropleth Maps, the Area Protocol. Let's introduce what is for sure the most common mapping algorithm for relative reference areas, things like states, provinces, or counties. I'm talking about the choropleth map. You see these literally everywhere, right? Especially during election season or in census reports. They are absolutely mandatory when you're dealing with data that normalizes a ratio to a specific area. Like, you wouldn't use a choropleth to map total population. That doesn't make sense. Instead, you'd use it to map population density, the number of people per square kilometer, perfectly filling those administrative borders with specific graded color schemes. But hold on, because here is where we encounter a major system vulnerability. It's a cognitive trap known as the area size bias. Get this, empirical studies show that the human detection rate for extreme data values plummets from 90% all the way down to roughly 60% when the geographic reference areas on the map are very small.
This quote right here perfectly highlights the danger. Physical size literally overrides data color in the human brain. Think about it. A massive, giant county with a really low density will unconsciously grab your attention and seem way more important than a tiny, microscopic county that's actually glowing with the highest density data. Your brain just straight up lies to you.
So, how do cartographers patch this visual glitch? Well, they force the map into equal area grids, transforming standard, messy boundaries into uniform squares or hexagons. Every single unit gets the exact same visual weight. Now, sure, it completely distorts true geography, but it presents the statistical data with absolute, unbiased purity.
Another really incredible way to patch these glitches is through asymmetric mapping. It's a step-by-step procedural transformation, kind of like an algorithm optimizing a digital grid. It takes that standard choropleth map, which lazily assumes people are spread perfectly evenly across a whole county, and injects real-world auxiliary data. It looks at where the lakes or unlivable forests actually are, and then recalculates the data for those exact optimized subareas. Now, what's really interesting about this slide is just watching the math in action. By excluding the empty spaces, like say that massive 800 square kilometer body of water marked with hatching there, the algorithm completely recalibrates the final visual output. The population density doesn't just drop to zero everywhere. Instead, it concentrates exactly where people actually live, pulling all that abstract data beautifully close to real-world habitability.
Let's shift gears. Section 5, Navigating Isoline Maps, Continuous Phenomena. What happens when data doesn't respect borders at all? Data that exists everywhere simultaneously, like air temperature or topographic elevation, requires a completely different rendering protocol.
Let's actually move to the visuals and see how this builds in a sequence. Imagine we want to map something continuous, like temperature. First, the system places raw value points, anchored perfectly to the center or centroid of our reference areas. Right now, it's just kind of a messy scatter of floating data nodes.
Next, the algorithm gets to work. It interpolates the empty spaces between those points. It draws these winding, continuous purple lines, which are called isoplex. These lines act almost like an energy grid, connecting areas of exactly equal value across the entire spatial continuum, completely ignoring any man-made borders underneath.
Finally, the system fills in the gaps. By dynamically coloring the regions between those drawn isolines, it creates this glowing, super readable isometric surface map. This is exactly the kind of data visualization you're looking at when you see a complex weather system or a continuous heat map on the evening news.
All right, we've made it to Section 6, Multivariate Cartography, Stacking Variables. We've reached the climax of our decision tree here. Because real-world problems are rarely simple, right? Often, multiple data inputs have to be rendered simultaneously onto a single geographic dashboard. But when you stack variables, let's say overlaying nominal, unordered data right on top of other unordered data, you are risking total visual corruption. If you just mix a blue layer and a yellow layer, you get green, and suddenly the viewer thinks they're looking at a completely new third data category. So, to maintain visual clarity, cartographers use distinct tactical combinations. They'll use a solid color hue for the base layer and maybe a distinct line hatching for the top layer. That ensures the two datasets coexist in total harmony on the dashboard without corrupting each other's message.
So, we've just explored the hidden architecture of the maps you use every single day. They aren't just pretty pictures, they are highly curated, mathematically optimized data interfaces. So, I'm going to leave you with this challenge. Stop being a passive map reader. The next time you open a map on your phone or see one in an article, ask yourself, what is this data actually trying to make me see? And more importantly, how is a cartographer designing the interface to make me see it? Keep questioning the data, and I'll catch you in the next explainer.